Hi everyone, I'm Chris Tisdell and thanks for tuning in. Just a few comments on this particular video. The original audio recording for this was lost, so what I'm doing today is basically adding some commentary of my own while I'm watching the video on my computer screen in front of me. Now this actually may be better than the original recording because here I can sit back and reflect on the original lecture. Anyway, I'm hoping you're going to like it. Now today's lecture is an introduction to the mathematics of series. Now what we're going to do is essentially introduce sigma notation. We're going to answer the question, what is a series? We're also going to talk about special series that you should know about, for example, like geometric series, and we'll also look at a simple series known as telescoping series. And we'll talk a little bit about important ideas like convergence of series and divergence of series. Now these are really important issues, and this is one of the main focuses of our investigation. Does a given series converge or does it diverge? Okay, so let's get back to some basic notation here. Sigma notation. Now you may have seen this at high school. If you haven't, that's okay. Now you can think of sigma notation as a simple way and a compact way of writing down the sum of a set of numbers. So here I've got the sum of all the natural numbers from 1 to 100, just added together. Now you can see on the left hand side I've got a sigma and a sigma sign next to an I. The I is known as the dummy variable. And you can see I've started the sum at I equals 1 and gone up to I equals 100. So in the sigma sign below and above, you've got the starting point and the ending point. Now the I here is just a dummy variable. There's another series there involving j. It's the same series. Now more generally, think of sigma a sub I, from, in this case I equals 1 to n, as just representing a finite sum. a1 plus a2 plus a3, etc. up to a sub n. Now the a sub I is a bit like a function, except it's just defined for whole numbers. Now think of a special case, sigma I squared from I equals 1 to n. So 1 squared plus 2 squared plus 3 squared up to n squared. That's a finite sum using sigma notation. Now as an independent learning exercise, see if you can add up all the whole numbers from 1 to 100. What do you get? This is a famous problem that was solved years ago by, I think it was Euler. Anyway, on to, that's a little bit about sigma notation. So let's get on to what is a series. Well, a series, an infinite series, it's just the sum of an infinite sequence of numbers. So here you can see I've got a1 plus a2 plus a3 plus, and just the 3 dots there mean we just keep on adding terms together. Now it's not like obvious how you actually add together an infinite set of numbers. So this is one of the ideas we're going to discuss. Now sometimes infinite series have a finite sum. So for example, think of the following sum: a half plus a quarter plus an eighth plus a 16th. And I claim if you keep on going, that'll all add up to 1. Now you can sort of see this if you look at the unit square, so a square of length side length 1, and you halve it, and you look at the area in that shaded half. So that area is 1/2 unit. Now halve the remaining area, so the second shaded unit will then have area a quarter, and if I keep on halving up, I'll get an eighth, and adding everything together will actually give me the area of the square. Now we know the area of the square is 1 unit, so the sum must add up to 1. Now there are other situations when you add up an infinite number of things and you get, it goes off to infinity. So 1 plus 2 plus 3 plus 4, obviously it's got to go off to infinity. And think about this, 1 plus a half plus a third plus a quarter, well, it's not obvious whether that's a finite sum or it goes off to infinity. Because it looks a lot like the one that I did with the area of the rectangle. But, you know, it's sort of, we're not quite sure what to do with that bottom series. Okay, so in general, an infinite series is denoted in the following way. So I've got this sigma a sub n, and I can start the sum at n equals 1 or any other number, say n equals 0 perhaps, and I sum up to, I just keep on summing. So to denote that, I put this infinity sign in the top of the sigma sign. Now what I mean by that is that essentially it's the limit of a finite sum. You can see this big N here as n goes to infinity. So you know, when we're dealing with these infinite series, we can't just keep adding up the terms and see what happens. It's just, you know, virtually impossible to do that. So what we do as a first step is to actually sum the first big N terms, where n's some number, and stopping, and then see what happens as big N goes to infinity. Does it approach some limit? Okay, now we call this S sub big N the sequence of partial sums associated with the series. Now, the big question here is, does this nth partial sum approach some limit? And if so, then what is it? Can we calculate it? So that's what we're going to look at in the next few slides. Alright, so here's basically all the definitions that you need on the one page, just for, you know, reference. So there's some important ideas here. We've defined an infinite series. We call a sub n, a sub little n, the little nth term of the series. And you can see how I've built this sequence of partial sums, S sub n, by, you know, I've just defined it down here. It's called a sequence of partial sums. Now, this is really important. If the sequence of partial sums converges to a limit, say some number big L, then we say the series associated with that converges to L. So in this case, the series would have a finite sum, and that finite sum would be whatever that number is, big L. Now, if the sequence of partial sums of the series does not converge, in other words, the limit of the sequence of partial sums doesn't exist, then we say the series associated with that diverges. So you can basically break down the convergence of a series down to the convergence of the limit of its partial sums. That's the main idea. So the big question that we are going to want to ask and answer today is, does a given series converge or does it diverge? We're not really interested in the value that the series converges to. Okay, and this is for a number of reasons. One of the reasons is that it is extremely hard to formulate or compute the value of an infinite series. It's very hard. It's very hard. So we're not really worried with that at the moment. So why do we want to know a given series converges? Well, one of the important benefits of a convergent series is that it will obey the rules of algebra. So we can add convergent series together and take convergent series away and things like this, and all the operations will be defined. Now, we will be able to determine the value of some certain series, like for example the one that we did a little earlier with the area of the unit square, but in general it's too hard. We're only going to look at a few limited cases. Now, divergent series do have their place in mathematics, and in fact Oliver Heaviside has a famous quote on that. He was given a series and he says this series is divergent and therefore we may be able to do something with it. This is typical Heaviside. He used to go against the grain, but for our purposes we'll be mostly concerned with convergent series. Okay, so you would have seen basic series at school, and we're going to talk about a really important idea called the geometric series. So the geometric series is just this following boxed series, and you can think of writing out the big nth partial sum in the following way. And what I can do is actually consider s sub big N and also consider x times s sub big N. So if you take one away from the other, you'll have a common factor of s sub n, all the terms will cancel, and then I can factor and rearrange to obtain a pretty formula for this big nth partial sum. Now, if we have a formula for the big nth or the nth partial sum of a series, then all we really have to do is take the limit. Does that s sub n approach a limit as n gets large and positive? If it does, well, that's the value of the series. The series converges. Now, a very important fact that you would have learned at school is the following formula for a geometric series. Now, the geometric series has the following sum if for all absolute x values strictly less than 1. So if I put any x value into this series, the box series down the bottom, then the sum will be c on 1 minus x, and where c is a constant. Like I said, that can be formulated from the working above. Now, this is a really, really, really important fact that you'll come across numerous times in university mathematics. So it's important that you just are able to state that off the top of your head. Let's look at an application of this idea. Let's consider the series sigma 1/2 all to the n for n equals, and we're summing from n equals 0 to off to infinity. Now, this is just a special case of the geometric series with x equals 1/2. Now, a half's between -1 and 1, so that series must converge to 1 on 1 minus 1/2. Big C's 1 here, and that's just 2. So we have complete information about this geometric series. Not only does the series converge, we know that the sum's finite, but we have the value that the series converges to. It converges to the number 2. But I need to say this is rare. We don't usually have that complete information about series. Well, there is one kind of other series that we can use this idea on and actually come up with a formula for the nth partial sum. And we can use that to actually calculate the value of the series. It's so-called telescoping series. Now, telescoping series basically have a lot of cancellation when you write out the nth partial sum. So this is one of these rare series where you actually can calculate the value of the series. So not only does it converge, we can find out what number it converges to. So what you can do with this problem is go to work on that 1 on n squared plus n. So we can rearrange that a bit, simplify it a bit, or put it in a more usable form. And then we can work out a formula for the nth partial sum. So what I'm going to do in this example is let a sub n be 1 on n squared plus n, factorise the bottom, and then use partial fractions to split up a sub n to two parts, basically. And then you'll see where the cancellation happens when we write out the nth partial sum. Okay, so here we're going to let a sub n be 1 on n squared plus n. So I'm just going to factor that. And what I'm going to do is break that up into two terms, basically. Now, you can do this a number of ways. You can use partial fractions and the, for example, method of undetermined coefficients, but there's a simpler way. If you just add n to the numerator and take n away, then you can break this up very nicely and very easily. So let me show you what I mean. So here I've added n to the top. I've taken n away, so I haven't changed it at all. And then I can break that up into two parts, and I'll get cancelling in both terms. Okay, so you can see now I've got two terms, 1 on n minus 1 on n plus 1. So what can I do with that? Well, what I'm going to do is write out the nth, big n, well in this case big nth, partial sum for that series. So we have the following. S sub big N is just, remember, A1 plus A2 plus A3, etc., up to A sub big N. So let's work out A sub 1. So A sub 1 is just going to be 1 on 1 minus 1 on 2. And I add to that A sub 2. So that's 1 on 2 minus 1 on 3. And let's add to that if we just keep on adding up to big N, I'll get the following. Now, if you look in each bracket there, well, just look at the first two brackets. You can see that the minus half in the first bracket and the positive 1/2 in the second bracket are going to cancel off. And the minus 1/3 in the second bracket is going to cancel with a positive 1/3 in the next bracket. I haven't written that down, but every term is actually going to cancel in this partial sum except the very first term, 1 on 1, and the very last term, minus 1 on big N plus 1. So this is one of the reasons why these series are called telescoping series, because you can kind of compress them like a telescope down to just only really two terms in this case. So let's calculate the limit of the partial sums. Remember, if this limit exists, then that's what the original series converges to. So here the limit is a limit of 1 on 1 minus big N plus 1. So as n goes to infinity, the second term will disappear and I'll get 1. So we have complete information about that series. Not only does the series converge, we have the value that the series converges to. It's 1. Okay, so this is one of the nice aspects of telescoping series or telescoping sums. Lots of cancellation. Now, we came up with some sort of formula for the big nth partial sum here. It was 1 minus 1 on big N plus 1. Now, in general, it's not possible to come up with these pretty formulae or representations for partial sums of series. Okay, it's just too hard. So what we need to do is actually develop a way of dealing with these series without relying on these partial sums and I guess a formula for these partial sums. So we need to develop other techniques and other methods that are much more easy to use. Right, so let's start our journey with a basic but very, very powerful test. It's called the nth term test. And basically it says the following. Well, if an infinite series converges, sigma a sub n, then the sequence a sub n must go to 0 as n gets large and positive. Now, if it's not really useful, that form of a theorem, so let me just rearrange it and use what's known as the contrapositive to write it in a more usable form. Well, what this theorem says that is if a sub n does not go to 0, then the series sigma a sub n must diverge. It cannot converge. So it's the same statement, just written in, I guess, a contrapositive form. Now, the nth term test is very, very powerful, but you can only use it to show a series diverges. You cannot use it to show a series converges. And this is the biggest mistake that students make with the nth term test. They apply it and they think that, oh, well, okay, if a sub n goes to 0, then the series sigma a sub n must converge. No, not necessarily. You just don't know. Okay? So I really want to stress that the nth term test is only useful when you want to show a series diverges. You cannot use the nth term test to show a series converges. It's just impossible. Okay? So let me give you an application of this nth term test. Let me show you how it's used. Here we've got sigma n all over 2n plus 3. So a sub n is just n on 2n plus 3. So let's look at the limit of this sequence, a sub n. So how do I evaluate this limit here? The limit of n on 2n plus 3 as n goes to infinity. Well, I look at the highest power. It's a rational, I guess, a rational type of function. So I divide by the highest power in the denominator. So the denominator has highest power 1. So I divide top and bottom by n to the power 1, and I'll get the following. Now, if I take the limit here, the limit's a half. Now, the limit of a sub n is not 0, half's not equal to 0, and therefore, by the nth term test, the series sigma n on 2n plus 3 must diverge. So notice in my solution here, I'm naming the test I'm using, because when you're doing these problems, it's very important to justify your methods and your reasoning. Okay, I'm clearly mentioning the nth term test in this solution. Okay, so what about a series where you can't apply the nth term test? The nth term test can't be applied to every series, because you cannot, let's say the series converges, you cannot use the nth term test to show a series converges. So let's just build a simple series, say sigma 1 on n. Now here, a sub n is 1 on n, and if I look at the nth term test and try to apply it here, well, the limit of 1 on n is 0. Now, all that means is that the conditions of the nth term test don't hold. So we can't say anything about that series based on the nth term test. The series might converge, the series might diverge, we just don't know. So because 1 on n goes to 0 as n goes to infinity, the nth term test tells us nothing about this series. So what we have to do is use some other method or some other technique to see whether sigma 1 on n converges or diverges. So that's one of the biggest mistakes students make. They try to apply the nth term test to show that a series converges. Okay, you can only use the nth term test to show that a series diverges. All right, so let's have a little play with this nth term test, and I've given you the following question. What's wrong with the following? So let's let S represent this series. So I've got sigma minus 1 all to the k from k equals 1 to infinity, and I've written some of the terms out. So it's 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 and so on. Okay, So if S is that, and I multiply everything by -1, I can just rearrange and bracket things up, and you see I've bracketed there and got minus S equals -1 plus S. So if I rearrange that and divide by 2, I get big S equals 1/2. So based on that, my series, big S, must equal 1/2. Well, what's wrong with that? What's wrong with that statement? Well, the problem here is that the series S, sigma -1 to the k, diverges. Okay? It diverges. So that, we need to be careful with using algebra and stuff on this series because it's a divergent series. Now, how do I know that series big S diverges? Well, it's the nth term test. If I let a sub n be, say, -1 to the n, here I've got k's, but it doesn't really matter, then what happens to a sub n as n gets large and positive? Well, it just goes -1, +1, -1, +1, so it oscillates. So the bottom line is that the limit of a sub n doesn't exist because it oscillates between -1 and +1. So if the limit doesn't exist, the limit can't be 0. So by the nth term test, the series must diverge. Now, this is a famous problem, I guess worked on by Nikolai Oresme, who actually used this series in a religious context, and he claimed that he proved the existence of God because you can actually use this divergent series to come up with some sort of contradiction like 0 equals 1. He claimed he proved something out of nothing. The important thing is that convergent series obey the rules of algebra, so you can add them together and take them away and multiply through by a scalar and things like this. Anyway, on to another very, very important test known as the integral test. Now, the integral test is going to be one of the fundamental tests that we're going to look at in this course, and basically it relies on the fact that a series, sigma a sub n, of non-negative terms converges if and only if its partial sums are bounded from above. Now, in this, I guess we're going to be mostly concerned with series with positive or non-negative terms. Now, because we're going to deal with series with positive or non-negative terms, we can think of their partial sums as representing an increasing sequence. Now, basically what we're doing is we recognise that each partial sum is obtained from the previous one by adding a positive number. Now down here, I've got some little rectangles where each of those rectangles would represent, A1, A2, A3, etc. And what you do is to get the nth partial sum, you just add the area of these rectangles together. They have sort of base 1 and height, or whatever the value, A1, A2, or whatever is. Now, we can use the corollary above to really see whether or not a series converges or diverges. Why is the above corollary true? Well, it comes back to an idea called the monotone convergence theorem. Now, the monotone convergence theorem says that a sequence that is bounded above by some number and a sequence that is non-decreasing must converge. Now, we don't spend a lot of time in this course talking about the monotone convergence theorem. It's a shame because it's a really beautiful result. But I guess sort of geometrically, you can see here that every time we add, in these rectangles, every time we add one more, we're forming an increasing sequence of area, if you like. Okay, well, onto the integral test. Now, the integral test is really, really important. It's going to be one of our main focuses. Let's look at the statement of the integral test. Suppose we have a sequence of positive terms, a sub n, and that a sub n equals f of n, where f is a function that's continuous, positive, and decreasing for all x greater than or equal to some number, big M. Think of big M as 1 if you like. Well, under those conditions, the conclusion is that, okay, well, the series and the integral, so the improper integral, either both converge or they both diverge. So in other words, under those conditions, the series and the associated improper integral have the same behaviour. Now, you would have seen improper integrals last semester, but the way you can actually prove this result is to just compare areas. So you can see here I'm shading in the area under the curve, f of x, and you can compare that with the area of these little rectangles all added together. So this is like the nth, I guess, similar to the big nth partial sum. Now, if we know the area under the curve in that blue sort of bounded region is finite, in other words, it converges, and it's greater than or equal to 0, then you can use we know the area in the rectangles is less than or equal to that integral. So if the larger integral is finite, then the smaller area of the rectangles has also got to be finite. Now, on the other hand, if I just draw my rectangles a little bit differently, you can see there's more area on the right-hand side of these rectangles than is under the curve. So if there's, in the limit, if there's an infinite area under the curve and the area in the rectangles is bigger than whatever the area under the curve is, it's got to push the area in the rectangles off to infinity, so that's got to diverge. So anyway, think about these. These two functions here, f of x, look similar, but they're actually different. Okay, in the first one, I'm thinking of something like 1 on x squared or 1 on x plus 1 all squared. And in the second case, I'm thinking of like 1 on x or 1 on x plus 1. So basically, the integral test can be formulated just by comparing areas. If I've got a finite area and I know something's smaller than that, well, the second thing has to be finite too. It has to converge in the limit. And if I have some sort of infinite area and I'm comparing it with something else that's bigger than that, well, that's got to be pushed off to infinity, so it's got to diverge. Anyway, on to some problems. Let's have a look at how the integral test works in practice. Okay, so here's some basic problems. The first one's very basic. Second one's a little bit more involved. But all it really involves in these questions is showing that the conditions of the integral test hold and then making an appropriate conclusion. So let's have a look here. I've got sigma 1 on n, and I'm going to let a sub n be my sequence, and I'm going to let it be defined by, say, 1 on n. And so my function, f of n, will just be 1 on n. Okay, so how can I take that and apply the integral test? Well, firstly, I need to make sure that the conditions of the integral test hold. So let's actually have a look at my function. Now, what I'm doing is I'm extending the domain of f to some sort of interval, say 1 to infinity or something like this. Okay? So f of x is just 1 on x, where x is greater than or equal to 1. So in the integral test, the big M will be, in this case, 1. Now, let's have a look at this graph. I can see that the function 1 on x is positive. It's also decreasing. and it's also continuous. This is all for x greater than or equal to 1. So let's write that down because they are needed in order to apply the integral test. And so after I've written this down, I can actually go through and look at the improper integral connected with our f of x. Now, students tend to like the integral test because it relies on integration, and most students are, by the time they take a course like this one, they've done a lot of integration. So people are pretty happy with the integral test. All right, so I've clearly recognised there that f's a continuous function, it's positive and decreasing all for x greater than or equal to 0. So all I really need to do now is to evaluate the improper integral associated with this function. So what I'm going to do is integrate 1 on x from 1 off to infinity. So basically, whatever this improper integral does, the original series will do the same. So they have the same behaviour. So if this improper integral converges, then the original series sigma 1 on n will also converge. If this improper integral diverges, then the original series sigma 1 on n will also diverge. Now, we're actually asked in the question to show that the series diverges, so we kind of know where we're going. Okay, so just to refresh everyone's memory, this is what we mean by an improper integral. We integrate over some sort of finite interval, and then we take the limit. So I've introduced this b, and I calculate the integral of what's in the big brackets first, and then the last thing I do is take the limit as b goes off to infinity. So let's integrate 1 on x. I'll get something like logarithm, a natural log of x. Now I don't need the absolute value signs around the x because x is positive. Now if I evaluate log, it'll be log b minus log 1, so I end up with log b. Now what's the limit of natural logarithm of b as b goes to infinity? Well, it goes off to infinity. Now I've been a bit naughty there, I've written equals infinity, I probably shouldn't have done that, but the point here is that the improper integral diverges, and so by the integral test, which I've named, the original series must also have the same behaviour, it must also diverge. So that's a real basic example. It is important to check the conditions on the integral test because you may try to apply it when you can't. And this is another common mistake that students make. Anyway, on to the second question. This is more involved. It's more involved because the integration is slightly harder, and you also have to show that the function is decreasing, and that takes a little bit more time too. So here I'm going to let the sequence a sub n be n on n squared plus 1, all squared, and I'm going to define that to be f of n. All right, so let's consider, extend the domain of little f to, say, a set of real numbers in this case. So f of x is going to be x all over x squared plus 1 all squared. And then I'll find some interval where that function is positive, continuous, and decreasing. Okay, so my function of x is just here, naturally sort of extended the domain on that, and I'm just going to restrict my attention to the interval x greater than or equal to 1. So my big M in this case is just 1. Okay, so I'm claiming now that this function f is positive. Well, that's pretty clear to see for x greater than or equal to 1. It's also continuous. That's no problem there because you're just dividing one polynomial into another polynomial, and the denominator has no zeros. And I also claim that the function's decreasing. Now, this is a little bit tricky to show, but what you can do is show that the derivative of f dash, which is, you can use the quotient rule to calculate this. You can show that this is actually strictly less than 0 for all x greater than or equal to 1. Now I'm going to leave that as something for you to do if you really want to go through and justify that. So what this means is that we've satisfied all the conditions of our integral test. So all we really need to do now is evaluate the improper integral associated with this problem. So let's consider the improper integral of f of x, which is improper integral of x all over x squared plus 1 all squared dx. Now, how do you integrate this? Well, there's a few different ways. I'm actually going to do this by substitution, or you can do it by inspection as well if you're strong on integration. It'll be something like, I guess, 1 on x squared plus 1, which you might have to play with. But to do it by substitution, you would let u equal x squared plus 1 and then calculate the differential and then make a substitution. So when I integrate this, I'm going to get something like minus 1 on u. And then I can just take the limit. Now I've sort of abused the notation here again. I should be writing out, I shouldn't be putting infinities on the right hand side of those brackets. But I think I was a bit rushed for time at this stage of the lecture. So the question is, what does this actually come out to? Well, if you take the limit as u approaches infinity, you'll get 0. And if you plug in u equals 2, then you'll get 1/4. So our improper integral converges to 1/4. And therefore, by the integral test, our original series must also converge. Now, it's really important to understand that the value of the improper integral is not necessarily the value of the series. Okay, usually they're different values. So I'm not saying in this solution that the value of the series is 1/4. Okay, that is not what I'm saying. So don't misunderstand that. I guess essentially that's a couple of problems. The first one's very easy. The second one is more involved. Okay. Well, that's some examples. Let's go on to a nice application of the P-series. Now, this is called a nice application of the integral test, and it involves a special type of series called a P-series. Now, basically, the following theorem tells us the following. Suppose I have a series that's sigma 1 on n to the p, where p's some fixed number here. So it might be sigma 1 on n squared, or sigma 1 on n cubed, or sigma 1 on n to the half, something like that. Basically, the following theorem says the infinite series sigma 1 on n to the p converges if the power p is strictly greater than 1 and diverges for all other values of p. So what this means is that sigma 1 on n cubed, the power is 3 here, 3 is greater than 1, this series must converge. So on the other hand, let's say we we're looking at sigma 1 on root n. So here the power p is power p equals a half. Now a half's less than or equal to 1. So by this p-series theorem, sigma 1 on root n must diverge. Now you should really know this p-series type theorem off by heart. So you should know, I mean, you can just quote it if you want, or refer to it. You can say, okay, well, sigma 1 on n squared's a p-series. P equals 2 greater than 1. This p-series must converge. Okay, you don't need to use the integral test there. You can just say straight out that, okay, this is a p-series and this is the value of its power. Well, if that power is greater than 1, the p-series must converge. If the power is less than or equal to 1, the series has got to diverge. So this is a very powerful test that allows you to tackle a whole bunch of basic series and immediately discover whether they converge or whether they diverge. Now, the proof of this result uses the integral test, right? Let's have a look at this. Basically, we divide the proof into two parts, when p's strictly greater than 1 and when p's less than or equal to 1. So let's apply the integral test and actually do a real short proof. It's only 2 lines. So, okay, well, if p's strictly greater than 1, then the improper integral will converge, and so by the integral test the series converges. And if p is less than or equal to 1, well, you can show again that the improper integral diverges, and so by the integral test the original series has got to diverge. Anyway, that's a basic introduction to series, geometric series, telescoping series and the integral test. Next time we'll talk about more in-depth ideas, for example like the comparison test and things of that nature.